Welcome to today's video. In today's video, we will be discussing some problems from the data link layer chapter. So let's begin. What is the maximum effect of a 2 millisecond burst of noise on data transmitted at the following rates? So the data is moving on with a bandwidth of 1500 bits per second, and the noise appears for only 2 milliseconds. So in those 2 milliseconds, how many bits of data are affected? So we'll just take this time, 2 milliseconds, and multiply that with the bandwidth. So that will give us, so if there's a pipe and data is flowing in that pipe, so how much data has been corrupted? So if you take the duration of the noise and multiply that with the bandwidth, it can tell you how much data might have been potentially got corrupted. So 2 milliseconds multiplied by 1500 bits per second. So if you adjust for the units, pay special attention to the fact that this is milli. So this is basically 2 by 1000 seconds, right? And this comes out to be only 3 bits. Since the rate of data flow is less, only 3 bits of information might have got corrupted. But if you increase the data rate to 12 kbps, so the k here is kilo, cancels out with the milli, right? And you get 24 bits. So now more data is potentially corrupted. And when the data rate increases like 100 kbps, 100 mbps, more and more bits of data get corrupted for the same amount of noise, for the same duration of noise. Byte stuff the following frame payload in which E is the escape byte, F is the flag byte, and D is a data byte, other than escape or a flag character. Okay. So wherever I see an escape character being part of the payload or a flag being part of the payload, I'm going to escape that again. So before this E, I added another E. Before this F, I added an E. These two E's are then added each with their own E's, so giving rise to 4 E's over here. And then this F also has its own E, right? This is how you byte stuff the following payload. Bit stuff the following frame payload. So anytime you have a 0 followed by 5 ones, as in this case, I've just counted the ones at the bottom here. So 1, 2, 3, 4, 5. After that, I add a 0. Then another such occasion rises here, where we have 0 followed by 5 ones, and there is a 0 there, we add a 0, and then again 0 followed by 5 ones, we add another 0 there. That is how you bit stuff the following frame payload. Prove that the code represented by the following code words is not linear. You need to find only one case that violates the linearity. So I've just cleverly chosen these two here. If I XOR the two values, so 0, 1, 0, 1, 0, 1, 0, 1, 1, and the rest 2, 1, 1, 1, 1 would give rise to two zeros. But this 1, 1, 1, 0, 0 is not part of this set, does not belong to this set of 4 code words, but this is not linear. In linear code words, if you take any two values and XOR them, whatever you get should be part of that same set, which in this case it is not. So this is not linear. Given the data word this and the divisor this, which is of 5 bits in length, please keep that in mind. Show the generation of the CRC code word at the sender site. Use binary division. Okay, so what do we have here? 5 bits in length for the divisor. So our remainder is going to be a 4 bits. It's always 1 bit less than the size of the divisor, right? So added 4 zeros to the end of the data word, and I'm trying to divide it by the divisor, right? Because I see a 1 here, I just add a 1 here, and it with 1, and just have 1 0 1 1 1 here. Now you leave out the leftmost bit here and start your XOR process from this bit. So 0 0 is 0, 1 1 is 0, 0 1 is 1, 0 1 is 1, and this 1 here is brought down to this level here. Now because we see a 0 here, I add a 0 here, right, and this entire divisor with zeros, and we get all zeros here. We ignore this leftmost bit. Start from this bit. 0 0 is 1, and that is how you keep XORing and you bring the next bit from the the data word, the thing here over here, and you bring it down, and then you see if this bit over here is 0 or a 1, and correspondingly just add the divisor by 1 or 0, and yeah, and you keep continuing the process until you run out of all the bits over here. And at the end, as you can see, just ran out of space at the page, the bottom here. So I've written the answer over here. It is 0 1 0 1. So I take 0 1 0 1 and add it to the end of the data word, and that gives me the code word. And very quickly, if you take this code word and there are no corrupted bits in the code word, and if this code word is divided by the same divisor at the receiving side, they should get a remainder of 0 0 0 0. If they don't get it, that means there is some kind of corruption in the transmission of this code word. What is the Hamming distance for each of the following code words? So you just look at the corresponding bits and figure out if those bits have changed. Here you have all zeros, but here you have just one of the bits have changed to 1. So the Hamming distance is 1. And similarly, you can do the rest of them on your own because it's very, very easy to do that. Assuming even parity, find the parity bit for each of the following data units. For even parity, even after adding the parity bit, the number of ones in the code word should be even. Okay, so here in the data word, we have 4 ones. So we should not add any more 1, because if you add another 1, it will become 5 ones in the code word, which is not even. So I've just added a 0 here. Here we have 2 ones. To keep it even, we don't add another 1, we add a 0. But here we just have 1. So we need to add another 1 to make it 2, which is an even number. But here we have 6 ones, so just add a 0 again to keep the number of ones even. This problem shows a special case in checksum handling. A sender has 2 data items to send, 4567. It's a 16-bit number because there are 4 hexadecimal symbols and each one is 4-bit. And BA98, 16 bits again. What is the value of the checksum? So I just take those two 16-bit chunks and add them. I just do ones complement addition, right? So if you do normal binary addition instead of doing hexadecimal addition, which is basically the same thing, you take the binary representation of 4, 5, 6, 7 and you'll get a 16-bit number. And if you take the binary representation of BA98, you're going to get another 16-bit number. And if you add them, you're going to get 16 ones at the bottom, right? Normal binary addition, which is basically representative of FFFF. But to find the checksum, what do? We flip the bits of the added thing here, which is if you take all ones and flip them, they'll all become zeros, which is 0000 in hexadecimal, because this 10 here is 0000 in binary. So right, you get 16 zeros out of this 4 hexadecimal zeros over here. So here you do not get any extra bit here on the left side. So when you add two 16-bit numbers, the result could be 17 bits, right? And because it can overflow, right? And if you take many 16-bit numbers and add them, then the result could be 18 bits, right? It could be even more than that. So what do you do with those extra bits? Because we can only work with 16 bits. So what do we do there? So whatever is left over on the left side, we bring them to the bottom here and we add them back, right? So if you have 16 bits on the right side here and you have 2 bits, we take those 2 bits and bring them to the bottom, and I've explained this in details in the theory videos, and you add them, and whatever you get, if that number is again 16 bits, there is no guarantee, even after that addition also it can become 17 bits, right? So you keep doing that, you keep taking the things hanging on the left side beyond the 16-bit boundary, bring them to the bottom, right? Add them, and whatever you get, until you reach 16 bits in size, keep doing that. And once you are stuck with the 16 bits, flip the bits, that becomes your checksum, right? At the receiving side, what do? You add everything, all the data chunks along with the checksum chunk, right? If, in this case, they're all going to be 16 bits in size, just like we did in TCP and UDP's case. And if you add all of them, you should get FFFF. Because if you get FFFF, and you flip the bits, you're going to get 0000, which is what is expected if there is no corruption. If there is corruption, then checksum may or may not be FFFF, because we have also seen in other videos, and I've given the logic for that. If you increase something maybe by 2 and you decrease another chunk by 2, the checksum is going to remain the same, because it's basically just a sum. You increase something by a certain amount and you decrease that something else by the same amount, the checksum can be easily fooled, right? So some ideas about checksums to keep in your minds. To understand why we need to have a minimum frame size, TFR. This is basically the transmission size of a single frame, and that is supposed to be 2 times the propagation delay, single side propagation delay. PSMA CD network. I'm sorry, there is a spelling mistake, as you know, as usual in your book, Forojan. They make a lot of silly errors like that. I just copied this question from that. So this is supposed to be CSMA CD, carrier sense multiple access collision detection, is what CSMA CD is for. So this D should be treated as an S. Assume we have a bus network with only 2 stations, A and B, in which the frame transmission time is 40 microseconds and the propagation time is 25 microseconds. Station A starts sending a frame at t equal to 0 and station B starts sending a frame at t equal to 23. Answer the following questions. Do the frames collide? Yes. Because if A starts transmitting at time t equal to 0, it is going to take 25 microseconds for the signal to reach B, because A and B are at the opposite ends and the propagation delay is 25 microseconds. So the first bit of A, right, the engine of the train, is going to take 25 microseconds to reach B. But before it reaches B, at 23, B also starts to transmit, right? So what will happen? So now at the time B starts to transmit, A's signal is almost at the doorstep of B, but like 2 microseconds away. So what will happen if B starts to transmit at that instant? They will collide at 24, right? Because they're going at the same speed. At 23, A is almost there near B, but B also starts to transmit, right? Not giving chance for A's signal to reach B, because B senses the carrier. A's signal is not there yet. It will need 25 microseconds to reach there. But at 23 itself, B senses the carrier, finds no signal of A, starts to transmit. So they will collide at t equal to 24. In 1 second, A will go half the distance left to reach B, and B will come towards A, and they will collide at t equal to 24. So yeah, they will collide. If the answer to part A is yes, does station A detect the collision? Okay, at t equal to 24, the collision happens. So it will take another 24 microseconds to reach A. So the collision signal, so here the collision has happened. That signal will take 24 microseconds, because it is 24 microseconds away from A. It will take the same amount of time to come and reach A. But will A detect the collision? No, because the frame transmission time is only 40 microseconds. So A will continue to transmit the frame from 0 to 40 microseconds, and then it will think that, okay, I am able to successfully transmit this frame. I did not detect any collision, because while it is transmitting, it is also continuously trying to listen for any collision signals. If it finds any collision signals, it is going to abort the transmission, and then it is going to retransmit after a random back off, right? But here, what's happening? At 40 microseconds, A thinks that, okay, I'm done transmitting the frame, and the collision signal has not reached it yet. It will need, so 24 microseconds after the collision happens. So the collision happens at 24 microseconds. It will take 24 microseconds to come to A. So at A, the collision signal will reach at 48 microseconds, as you can see. And at that time, A has already finished transmitting the frame. So A will not detect the collision. So A's data is corrupted forever. A has transmitted and it has not waited to detect the collision. If the transmission time, the frame transmission time had been longer, let's just say had it been 2 times TP, that is 50 microseconds, then A would have been transmitting the frame until 50 microseconds, like, where is my mouse cursor here? Around that area. So at 48 microseconds, when the collision signal reaches A would have been still transmitting the frame. Then A could have detected the collision. But now it cannot because it is done transmitting the frame. Okay, if the answer to part A is yes, which it is, does station B detect the collision? Yes, station B is going to get the collision because station B starts to transmit at 23 and it will be transmitting until 63. Why? Because the frame transmission time is 40. So it starts at 23, so it will be transmitting until 63. So when will the collision signal reach B? It has happened very close to B. So it will reach B pretty quickly, right? It is only 1 microsecond away from B. So it happens at 24, it will be reaching B at 25. At 25, and 25 is between 23 and 63, right? At that point of time, B is still transmitting the frame. So B is also listening on the channel whether a collision signal has arrived. When the collision signal arrives, B will detect the collision, abort the transmission of the frame and retransmit the frame at a later point of time. Assume that there are only two stations A and B in a bus CSMS CD network. The distance between the two stations is 2000 meters and the propagation speed is 2 into 10 to the power 8 meters per second. If station A starts transmitting at time T1, does the protocol allow station B to start transmitting at time T1 plus 8? If the answer is yes, what will happen? Okay. Let's figure out the propagation delay, and the propagation time, the one-sided propagation time is going to be the length of the link divided by the speed of transmission, comes out to be 10 microseconds. And please pay careful attention to the units. Okay. Here the meter and meter cancel out. The seconds kind of goes to the top here. And the 3 zeros here kind of make this 10 to the power 5 at the bottom. Right, so if I multiply it by, and the 2 and 2 cancel out. So if I put a 10 at the top, which is this 10, at the bottom it becomes 10 to the power 6, which if you take it to the top, it becomes 10 to the power minus 6, which is a microseconds, right? Very fundamental, please keep it in mind. So the propagation delay is 10 microseconds and A starts transmitting at T1. So the signal will reach B at T1 plus 10, okay? It will take 10 microseconds for the first bits, the engine of the train, right? The head of the train to reach B. It will reach B at T1 plus 10. So at T1 plus 8, what will happen? If B tries to send something at T1 plus 8, it will sense the channel and it will find the channel to be idle because A's signal has not reached B. It will take 2 more microseconds for it to come. So B can start transmitting. Now what will happen? Will they collide? Yes, they will collide because A's signal has not reached B. So B starts transmitting and they will start to collide at T1 plus 9 because the signal is just 2 microseconds away from B. So A's signal will go 1 microsecond to the right and B's signal will come 1 microsecond to the left and they will collide exactly at T1 plus 9. Yes, they will collide. Just like the previous problem. Does the protocol allow station B to start transmitting at time T1 plus 11 microseconds? If the answer is yes, what will happen? Well, it depends how big the frame of A is. If A's frame is very long, so it will reach the first bit of the signal will reach B at T1 plus 10 because T1 is when A started to transmit and 10 is the propagation delay. So it will come and it will reach B at T1 plus 10. But then for how long will it take for the entire signal to go away? Well, that is the transmission time. That is the length of the train, right? Behind the engine. So if that is less than 1 microsecond, then what will happen? Between T1 plus 10 and T1 plus 11, that small frame will pass B, okay? And then when B starts to transmit at T1 plus 11, that frame would be gone. Then B will find the channel to be idle and it can transmit. But if the frame size is more than 1 microsecond, then at T1 plus 10, the frame will reach B and it will, at T1 plus 11 also, that frame would still be present around B, A's frame. would still be around B. So when B senses the carrier, it finds the channel to be consumed, to be busy by A's data. So it cannot start to transmit. In CSMA, we do not allow that. We first sense the carrier, and if it is only idle, then we can think about transmitting, depending on the persistence methods, right? Okay. If an Ethernet destination address is this, what is the type of the address? Well, you look at the first byte here, which is 07, and it is clearly odd. 7 is an odd number. It's going to be 00000111, and the least significant bit of that is 1 because it's an odd number, and that happens to be a multicast address. If it is even, then it is unicast. And if all the bits here are ones, that is, this is all filled with F's in hexadecimal, and that is a broadcast address. So there are two stations A and B in a CSMS CD network. Assume that stations A and B each have a frame to send in the collision interval 2 into TP. So that is the collision interval, right? If you start transmitting something, then if someone else transmits in that brief period of time, well, it may be brief, it may not be brief. Usually propagation times are very less. In that brief amount of time, if someone else also transmits, then a collision can happen, right? So no one else should be transmitting at that in that duration of time. That is a vulnerable time for a CSMS CD network, as we have studied before. And A and B have frames to transmit, and the probability of them transmitting that frame in that duration of time is P1 and P2 respectively. That is, for A it is P1, for B it is P2. Answer the following questions. If P1 is 0.3, it has got a 30% probability of transmitting, and B has a 40% chance of transmitting because P1 is 0.3 and P2 is 0.4. What is the probability of success for station A? A will only succeed if B does not transmit. And what is the probability of B not transmitting? It is 40% that B will transmit. So it is 60% that B will not transmit. And here the probability of success is a conditional probability is what I found out here. It is given that A transmits, right? A transmits. Given the fact that A has already transmitted, what is the success for that frame to go uncorrupted? Please keep that in mind. If this is not a conditional probability, then we have to also multiply this number with 0.3. It is like the probability that A transmits, it is 0.3, and the probability that B does not transmit, which is 0.6. You have to multiply those two numbers. So that is the pure probability, like starting from 0, right? We find out if A's frame reaches the destination successfully. For that, you have to look at whether A will transmit or not. If A does not transmit, then it cannot send its frame successfully. And even if it has transmitted, if B transmits at that in that period of time, then also A's frame cannot reach. So here I'm assuming A has transmitted. So I'm not taking the 30% probability here. A has already transmitted, but B should not transmit. That is why I've just taken the probability of B not transmitting, which is 1 minus its probability of transmitting, which is 1 minus 0.4, 0.6. Similarly, what is the probability of success for station B? We're assuming B has already transmitted and A should not transmit. So we have 1 minus the probability of A transmitting, which is 1 minus 0.3, which is 70%. Now, what is the probability of success for a frame? For here, I have combined the probabilities. So just read it like this, right? So the success for a frame is A transmits and B does not transmit, or B transmits and A does not transmit, right? 30% chance that A transmits and 60% chance that during that time B does not transmit, which is 1 minus 0.4, or 40% chance that B transmits and 70% chance that A does not transmit, which is 1 minus 0.3. And if you add all of that, you get a 46% chance of success. And again, keep in mind for bits A and B, I'm assuming that the nodes have already transmitted the frame. Okay. So I'm not multiplying this 0.6 by this 0.3, which is the probability of A even starting to transmit the frame. So I've done conditional probabilities in A and B and found out a pure probability in bit C. We have a pure Aloha network with a data rate of 10 Mbps. What is the maximum number of 1000 bit frames that can be successfully sent by this network per second, right? So we know that 18.4% is the best utilization you can get out of a pure Aloha network, right? That is the maximum efficiency that you can get. So the channel can carry data at this rate, 10 Mbps is what I've written here. If the efficiency was 100%, then how many 1000 bit frames could we have transmitted per second? Well, we take the bandwidth divided by the size of the packet. But we can only transmit 18.4% of that because it is a pure Aloha network. And the answer comes out to be 1840 1000 bit frames per second, because the rest of the frames would probably get corrupted because of collisions. In a CD, again, there is a mistake here from the book. It's supposed to be CSMA CD network with a data rate of 10 Mbps. The minimum frame size is found to be 512 bits for the correct operation of the collision detection process, right? So why is there a minimum frame size? Because if there is not a minimum frame size, then there will be no minimum frame transmission time. And if you transmit any frame that is smaller than this size, what will happen? As we saw in that problem, in the problem before, in which A's frame was smaller, it finished transmitting it in 40, whatever the unit of time there was. But the collision reached at 48 and A was not transmitting at that point of time. It was not in a position to detect that collision. So we have to have a minimum frame size, right? Because that guarantees a minimum frame transmission time. So what should be the minimum frame size? If we keep the size of the network constant, then the length is kept constant, the propagation delay is constant, but increase the data rate. Now the data rate, the bandwidth has increased. So now the same 512-bit frame, if you increase the bandwidth, the transmission time will decrease, right? Because what is transmission time? It is size of the frame divided by bandwidth. If you increase the bandwidth, the denominator increases, the frame time will go down. But we need a minimum frame time. The minimum frame time should be 2 times the propagation delay. So from 10 Mbps, if the bandwidth increases to 100 Mbps, and if we assume the original frame size to be alpha, which is 512 bits, now if the bandwidth has become 10 times, then the frame size should also become 10 times. Only then the frame transmission time will remain a constant and the system will still work, right? And here it has become 100 times. So we increase the frame time, the frame size to be 100 times the original frame size. Then what will happen? Size of the packet divided by bandwidth will still remain, whatever the time will be, at least be equal to or greater than equal to 2 times propagation delay. And if it becomes 1000 times, then the frame size should be alpha into 1000, because 10 Gbps is 1000 times of 10 Mbps. How does the Ethernet address this appear on the line in binary? So we know that the addresses kind of go left to right, as in 1A will go first. But this 1A, if you write it in binary, the least significant bit will go first, right? So if you write 1A in binary, what are you going to write? 1 is going to be 0001 and A is 1010, right? So look at this, 0001, 1010. If I flip it, it is going to look like this, 0101, 1000. It's like, show it on a mirror or something, then the left and right kind of flip, right? That's exactly how it goes. And look at 6F, it goes at the last. But what is F? 1111, and those ones appear here on the left. And what is 6? 0110, which is a palindrome. So it is 0110 over here, right? So it goes from left to right, but each of those bytes kind of go right to left. Like least significant bit of that byte will go first and in that order, right? Okay. A router with IPv4 address this and Ethernet address this has received a packet for a host destination with IP address this. So router has received a packet. Now it wants to forward the packet to the correct destination, but it does not know the hardware address of that destination, right? It knows only the IP address, which it actually finds from the destination IP in the IP packet. So the entries in the ARP request packet sent by the router also encapsulate the packet in an Ethernet frame. So the Ethernet frame begins with a preamble and the start frame delimiter, as we all know. Then we have the destination address, and the router does not know. It just broadcasts this Ethernet frame throughout the network. So we have all apps over here. That's a broadcast Ethernet address. Then it puts the source hardware address, which is its own address, which is 2345, and 2345 is given here in the question, ends with CD. Then we have the type, which is basically for ARP, it is going to be 0x0806, which is what the type that Ethernet frame store for ARP packets coming from the above layer, which is for multiplexing and demultiplexing purposes. When this Ethernet frame reaches the destination, it will look at this type and say, okay, so the data inside this Ethernet frame needs to be sent to the ARP protocol in the network layer. Otherwise, it won't know whether to send it to IP, ARP, whom to send it, who will process this, right? This is how you can demultiplex. Then we have the data, and the data here itself is the ARP request packet, right? Here, this is the hardware type is 1, the network type is, and one hardware type is for Ethernet, and 0800, the network layer type is for IPv4. We have 0x06 is 6 bytes per physical address, 0x04 is 4 bytes per one IP address, and the 1 here is because it's an ARP request. And then we have the source hardware address 2345. This is the router's hardware address, and this 0x7D 2D170C is, I've just taken the routers, which is basically the sources IP address 125.45.23.12. I've converted that to hexadecimal and written there, because 125 is going to be 7D, this 12 is going to be 0C. That's how I've taken each of these octets and converted each octet into 2 hexadecimal symbols each. Here we go for the destination physical address, which is not known, so we fill it up with zeros. That is exactly what ARP will help us to do, right? And then we have the destination's IP address, which is given here, which is again 125.11.78.10. I have encoded that in hexadecimal and put it here. In the end, you have the CRC, which I have not calculated. It is going to be a 32-bit CRC, right? This is how the Ethernet frame is going to look with a payload that is an ARP request packet. An Ethernet MAC sublayer receives 42 bytes of data from the upper layer. How many bytes of padding must be added to the data? We know that the minimum size of the payload for an Ethernet frame is supposed to be 46 bytes. So if you send 42 bytes, you need to add 4 bytes of padding to make it 46 bytes. What is the ratio of useful data to the entire packet for the smallest Ethernet frame? Well, the smallest Ethernet frame will have only 46 bytes of useful data, because that is the minimum that is allowed. And if you add the addresses and the types and CRCs and all of these other things, it will become for 46, and you add these addresses, right? 6 bytes, 12 plus 2 is 14, and CRC is 18. So if you take the minimum payload size of 46 and add 18, you get 64, right? And so the ratio is basically 46 by 64, which is 0.72, and there can be more numbers beyond that. I just truncated that to 0.72. Thank you.